All right, welcome to the spreadsheet adventure where we carry out Euler's method using a spreadsheet. And here I'm using Google spreadsheets, that's what they're called, yeah, because they're available to everyone, I guess. But you can use, Microsoft Excel or LibreOffice or whatever. So the idea is to, for this example demonstration, to show you how to get a numerical solution to this differential equation here, for which I have an analytical solution over here, which I got with the method of integrating factors. So what I do in the spreadsheet is, my hope is to generate a plot of a solution in the spreadsheet without using this, without relying on all of the method of integrating factors stuff that I did up here. So without solving the differential equation at all. And basically what we're going to do is use the columns of the spreadsheet to generate the Euler method rows here to create these Euler steps. So let's start with actual columns for time, value of x, the value of x prime. Yeah, let's do that. And let's center these. And let's pick a time step. So the initial time is going to be 0, right? And then the initial value of x I put in here somewhere. This is my initial value problem that I'm going to demonstrate, and it has initial value of x being x of 0 equals 1/2. So I'm going to put 0.5 here. So I already know some information about this first row. Then how do I get the second row? Well, the next time is going to be the previous time plus the time step, right? So I'm going to put the time step somewhere. Let's say I put the time step in this cell, F2, right? And I chose cell F2 for the time step. So let's call this delta t. And these are just some words that indicate where delta t is going to be, so I can find this cell when I want to. And let's make it 0.1 to start with. So I could just put the number 0.1 here rather than putting it in a cell, but I'm putting it in a cell so I can play with it later. So I can modify what's in this cell and change the time step. So now I can drag this, and it didn't work. So the problem here is that if you stare at this formula, look at this formula, how it changes as I go down here. It's A3 plus F3, A4 plus F4. I don't want the cell here to change, right? I want it to always focus on this cell. But when I drag this cell down, it's like updating the row that it's drawing this value from. So to prevent that update, to refer to that, let me undo here the extension of the cells, to refer to this cell without allowing it to change when I drag this thing. I don't know if there's official terminology to what I'm saying, but basically if you put $, if you put a $sign in front of F, it sort of freezes that what I'm referring to here comes from column F. If you drag the cell to the left or right, don't change the column. And the $sign 2 says freeze the row at 2. If you drag the cell up and down, then don't change the row. So this particular cell evaluates to the same thing, but now if I drag it down, then you see it behaves the right way. And if I scroll through here, watch the A is changing, the row of the first part is changing, A7, A8, A9, etc. But this is frozen, right? Really, you only needed to freeze this. You don't need to freeze the F, but whatever. Okay, so there's our time columns. And if I change this, then it'll update. So if I make this like 0.2, then now time increments in 0.2 sized steps. Okay, so I can just update this and watch everything change live. That's the nice thing about a spreadsheet. Let's actually extend this to be very long. About, I don't know, 200 rows. Sounds good. That way I can look at time step 0.1 and time step 0.01, and time step 0.01 will at least give me up to about 2. Let's take it to actually up to 2 units of time along. Okay, so let me start with it at 0.1. Now, how does x change? Well, so the way the Euler step works is that each value of x is going to depend on the previous value of x and the previous value of t and the previous x prime. So it's going to be how to put this? So what I'm going to type in here, what I'm going to type in here is basically this, that the new value of x equals the previous value of x plus the instantaneous rate of change of x from the previous row times the change in time. So this is new value of x equals old value of x, so the cell right above, plus now here in print, plus the rate of change of x, which I'm going to put here soon, times the change in time, which is the delta t. And again, I want this to be frozen so that it doesn't change when I drag this thing down. So that's the idea. And right now it's saying that there's no change, that x goes from 0.5 to 0.5. That's because I haven't filled in x prime, so it's treating it as though it's 0. That makes sense, right? If x prime were 0, then you would expect x to not change in our approximation. But now let's put in what x prime actually is. So x prime, now this part is not an approximation. This is exactly correct. According to the differential equation over here, x prime is always 3x minus t. That's what this differential equation says. So it's going to be 3 times whatever x is minus whatever t is. Now let me drag this down so that it fills in. Okay, so I hope you're getting kind of a visual for how different cells depend on other cells. The x prime always only depends on the x and the t. That's what the differential equation tells us, how x prime can be determined from x and t. So these two determine this. Then these two will determine this. These two will determine this, and so on. All right, and we're getting a bunch of nonsense there, of course, because it's treating all of these as zeros. I haven't filled them in yet. So while each x prime is determined by the things in the same row as it, each x is going to be determined by what's above it, right? So this is determined by that and that, and that. No, just that and that. So this depends on these two. This will depend on these two. This will depend on these two, and so on. So let's drag this down. Okay, and I'm seeing some very large numbers down here. Not a big surprise. If you remember from the Mathematica plot, it looked like it was a sort of exponential growth, pretty much, is what we had. And if you look at our solution here, this is mostly dominated by this term that's going to grow exponentially, e to the 3t. Let me fix the zoom here. Okay. So my goal is to see basically the plot of this, but not actually having to type this in. Okay, so I think we're basically done. Let's just make sure this works, that the formula looks correct. So this one is, this x is b2, so the previous x, plus c2, so x prime times delta t. Then I go to the next one. It becomes b3, c3, so these two determine it. This one, b4, c4, so these two determine it. Looks like it extended correctly. So there's our numerical solution. This is our numerical approximation. The initial condition is satisfied. Of course, it's satisfied exactly because we literally just typed in the initial condition. And then according to this, this numerical method, at 1 unit of time, this is the value of x. So when t is 1, this is what it predicts x is. When t is 1.6, this is what it predicts x is. Now what about the exact values? Can we compare this to exact values, the theoretical ones? So this is numerical. Let's look at x theoretical. So this is what I got without ever solving the differential equation. All I did, the only way in which I even used the differential equation is that I typed it in here basically when I was defining these cells. Okay, so let's try to fill in this column with x theoretical. So let's see. X theoretical, I solved for and I got an explicit function of t. So each time it'll only depend on t. This will depend only on this, and so on. So this will be, let's see if I can display both. This will be 1/9 plus 1/3 times t, which is this cell, plus 1/2 minus 1/9 times the exponential. Exp is the exponential, apparently. 3 times t, which is this cell again. And now as I drag this down, these a2s are going to become a3, a4, etc. So drag it down. Okay, and look at this. So the initial condition is satisfied, not a big surprise. The C was chosen here earlier to make the initial condition be satisfied. So that's a good sign. And you can see after one time step, after 0.1 units of time, this is the numerical prediction, making a linear step along the slope of 1.5. Is the numerical prediction is that at time 0.1, x will be 0.65. The true value, however, is this. So you see there's a small error. It's off by a little bit. If I make a smaller time step instead of 0.1, 0.01, then it'll be off by less. So this is time 0.01. This is the theoretical value. This is the numerical value. They're quite close, actually, right? But yeah, so you can see that. Let's compare two values at time 1, say. So at time 1, the numerical is 5.8 apparently. The theoretical is 8.2. At time 2, the numerical is 74.6. The theoretical is 157. Look at the large. Look at how far off they got from each other. Like here, they're just like 3 apart, basically, right? And here, they're well over 50 apart. So you're seeing that the error accumulates as you go down. Each of these positions depends on the previous one, and each time you accumulate some error. And if I make the step size smaller, like if I make it 0.01, say, then I have to scroll down further before I get to time 1. So that's here. And now you can see the theoretical is the same as it was when I had this as 0.1. So remember this number here, 8.2554, 8.255. 0.01. Now I have to scroll down much further to get to it, but here it is, 8.255. But you see this is much closer. Before it was 5 point something, now it's 7.9. So making smaller steps in time makes your prediction end up being more accurate when you use the numerical method. Okay, let's make some plots. So I did not know how to do this until I played with it a little bit. So insert chart. And let me see if I can do this in a way that doesn't leave my face blocking everything. How about I move my face to down here. So let's see. So I'm going to switch the type of plot that it is. So if you're using Microsoft Excel or LibreOffice or something else, then you'll have to figure out how to do it with that. And I'll add an x-axis and select a data range. Then I should be able to highlight it. And instead of dragging this all the way down, let me take it to row 202, which is where I think it went up to. And for some reason it got added as a series, not an x-axis. Okay, anyway, let's add a series, which is going to be, let's plot the theoretical one first, up to row 202, and there it is. This should look like the mathematical plot that you saw before, running out to time 1, running out to time 2 here. Yeah, it just looks just like the mathematical plot, right? What you're seeing here is the plot that does use the method of integrating factors. It's a plot of this, because I used this column, and this column just filled in my analytical solution. Okay, now for the numerical. So let me add another series and select this range and run it out to 202. And there. So the red one, I guess, is the one that just got added. That red one is the numerical, is the one we got with Euler steps. And you can see it's not perfect, right? It's a little bit off, away from perfect. Now I want to be able to see what happens when I change the delta t. But I think so the chart should update if I change this delta t. And it does update, but unfortunately it also changes the range of times that it displays, because it's displaying all rows, and the same number of rows covers more time if the time step is larger. So let me change it back and try to force the horizontal axis to display from time 0 to time 2, no matter what. And let's also force the vertical axis to stay the same. 0 to 200 is what it is now, so let's keep it that way. Okay, now let's see if this works. Oh, and while I'm at it, in case you use this to actually put plots into your, in case you use these plots in your final write-up, you can give the axes some titles. So horizontal axis, let's call it T. Vertical axis, let's call it X. So now it says TX here, which is nice. And I fiddled a little bit with legend, but I couldn't figure out how to get a nice legend. I see some little colors here. They should have some labels, but I just didn't bother with that. Maybe you can figure that out if you want to. Okay, so now I should be able to modify this. So let's make the step size, so hopefully this time and x remain the same. Let's make the step size smaller or larger. So this will be a more crude approximation because it's making larger steps, larger time steps, and traveling along linear slopes for longer periods of time. Okay, there we go. So again, the red is the numerical approximation, is what we got from the Euler method, not from solving the differential equation, and the blue is what we got from solving the differential equation. You can see the gap here, by the time we reach 2 units of time, this is quite a large gap, right? Compared to when I do a smaller time step size. So another thing I can do, let me get rid of this. So remember the differential equation had this 3 here. That's because I just fixed r at 3. And I do have to fix a number here in order to have actual numbers that go here, right? It's not going to do it algebra for me and put r's in different places if I want to see how everything depends on r. But what I can do is make r be some thing like delta t that I can just play with and see how it affects things. So let's start it at 3. Let's see how would I incorporate r into things. So the 3 shows up here in my way of calculating x prime. Each row determines x prime based on the t and the x that go with it. So how about here I put r instead of 3. So this, oops. So here instead of 3, I'll put this, the content of this cell, and I want it also frozen. Now let me extend this pattern all the way down. And let's see, now if I change this to like 4, hopefully everything changes. Yeah, you can see what happens. So it's recalculating all of these numbers every time I change things. 3.1 versus 3 versus 2 versus 1. So actually 1 is kind of interesting with this. I think it ends up going negative, and then shooting down. If you look, yeah, so if you just stare at the number, I don't want to play with the plot range anymore, but if you just look at this, it kind of grows and then it starts shrinking again. See, and then it goes negative, and then it starts a decline. It's pretty interesting. So why is that happening? Well, in the original differential equation, you've got these kind of two competing things, the population growth, style growth, right, like exponential growth, and then you also have this. If you make r very small, then you can have this eventually how to put it? So this term causes x to increase, and this term causes x to decrease, right? Early on, if x starts at a small number, which for us it starts at 1/2, if r is small, then this is not giving us very much of a rate of increase. But it will lead to exponential growth of x, so this term will grow exponentially. But if r is small, then the longer you let time run, the bigger this term gets. If r is small, then this might catch up to that in some sense. It's just kind of interesting. Maybe we can see if we change the vertical range to allow for negatives, like negative 200. Maybe that's a little too much. Yeah, so you can see it crossed below 0 there. Okay, so that's it for the spreadsheet version of how to do the Euler method.